Good morning,
We'll give
everyone.
you a warning about 5 minutes before. So you have 12 minutes for the talk plus 3 minutes for.
Perfect. Perfect.
We'll give
Thank
you
you.
warning at
Yes,
around 7 or 8 minutes.
sounds good. So good morning, everyone, or good evening here in California. So I'm Ethan. First, just want to thank the organizers for having me, particularly Subinoy, who I've been collaborating with over the last year or so, and I'll actually mention some of the work I've been doing with him. But I'm going to tell you about the recent work we've been doing over the last several years to use dwarf galaxies to constrain dark matter microphysical properties, and particularly I'll focus on fuzzy or axion like dark matter, since it's one of the topics of this conference. So we've heard plenty of motivation. I just want to briefly recap why observations of small scale structure are interesting to probe the nature of dark matter. So this is a very nice plot from a review paper by Buckley and Peter that shows many of the dark matter models, including many of the ones we've been talking about, fuzzy dark matter, axions, PBHs, in this parameter space of the coupling to the standard model of dark matter on the x-axis. And on the y-axis is what I'll call the minimum halo mass. So this is the mass of the smallest gravitationally bound dark matter halo that can form in a particular dark matter model. And the point is that, depending on the microphysics of dark matter, the minimum halo mass generically differs, right? So if we can measure the smallest halo in the universe, right? If we can answer the question of what that halo mass is, then we automatically learn quite a bit about the microphysical properties of dark matter. So a kind of obvious question to ask is, what is the luminous content of these very small halos? And in fact, we've, in recent years, particularly detected many faint galaxies in the local universe. So these are dwarf galaxies and the so-called ultra-faint dwarf galaxies. So this plot shows every known galaxy in the universe out to 6 megaparsecs, so within the local volume, as a function of distance and brightness on the y-axis, with fainter galaxies towards the bottom of the plot. And what you'll see is there's a very clear selection effect such that we can only detect the very faintest galaxies, the so-called ultra-faint dwarf galaxies, within the virial radius of Milky Way halo. So these ultra-faint galaxies occupy the smallest luminous dark matter halos, and to kind of turn the usual framing of the small-scale structure problems around, right? If we can understand the halos that these galaxies live in, we actually automatically access quite a bit of information about the dark matter particle. And luckily for us, the observations in this field are really rapidly advancing. So there are now more than 60 known Milky Way satellite galaxies. That number has doubled twice in the last 2 decades. And one of the efforts that has really driven up that number is the Dark Energy Survey, which are shown in red here, the dwarf galaxies discovered by DES. And those are all in the kind of vicinity of the Large Magellanic Cloud. And in fact, many of these galaxies are satellites of the Large Magellanic Cloud itself that accreted into the Milky Way with the LMC. So with these wonderful observations, right, we kind of have a challenge, right? We have to answer, like, are these consistent with CDM on these extremely small scales, or are these pointing to evidence for non-CDM physics? So just to review how this works, right? If you run a high resolution cosmological zoom-in simulation of, say, a Milky Way mass halo, in CDM, of course, you form structure all the way down to the free streaming scale, down to roughly 10 to the minus 6 solar masses in WIMP-like dark matter. But of course, if you start changing the microphysical properties of the dark matter particle, then you generically change the minimum halo mass. So this is an example in warm dark matter, where kind of large free streaming length suppresses the above halos below some characteristic mass. And so the game, of course, is just to count galaxies, count these number of detected ultra-faint galaxies and compare them to the predictions of the simulations, accounting for the fact that our current observations are highly incomplete. And if there's one thing I want you to take away, it's that there's no missing satellites problem, at least as far as the Milky Way satellite galaxies are concerned. And several studies have reached this conclusion over the last few years, both from the perspective of hydrodynamic simulations, which predict satellite populations that are actually in good agreement with the observations, or just from the perspective of populating halos in a simulation with an empirical model that relates, galaxy luminosity to halo mass, for example. So, this is a really key conclusion, But importantly, this fact has only been demonstrated at fixed modeling assumptions. So for example, at fixed assumptions about the subgrid physics in hydrodynamic simulations, or at fixed assumptions about, say, the stellar mass-halo mass relation that's used to populate halos in empirical models. And moreover, it's only been demonstrated for the brightest half of the Milky Way satellite population, so not including those ultra-faint dwarf galaxies detected by DES that I just showed you. So that's what led us to develop this framework over the last several years, along with many in the Dark Energy Survey and Risa Wexler and others. And essentially what our framework is kind of a simulation-based inference. So we run many of these simulations of Milky Way-like halos at extremely high resolution. So many millions of CPU hours go into these. And these simulations are constrained to have Large Magellanic Cloud analogs, similar to what is observed in the data, so that you naturally predict this population of LMC satellites. These are combined with an empirical model for the galaxy halo connection that is parametric, such that it can be statistically fit to the observations, for the population of detected galaxies in each survey footprint. And this is really key. We actually, to forward model these galaxies, we apply satellite detectability functions that are directly constrained by the photometric data. So this is really kind of an apples to apples comparison. Okay, so now what we want to know, there are many wonderful things that we've learned about the galaxy halo connection by doing this, but what we want to know here is, what does this imply about dark matter microphysics? And what we can do is, run these fits using simulations or using analytic functions to estimate the suppression of the subhalo mass function in non-CDM models. So the idea is that you start with some transfer function, right, a ratio of the linear matter power spectrum to that in CDM, which depends on the microphysics of dark matter. So we can just focus on the fuzzy dark matter curve here, since that's what I'll talk about. If you run a simulation of structure formation, or if you have an analytic way to calculate a collapse of halos, this transfer function translates into a suppression of the subhalo mass function relative to CDM as a function of halo mass, right? And finally, that kind of manifests as a suppression of the satellite luminosity function of detected dwarf galaxies, such that, if the cutoff in the power spectrum is at too large of a scale, then it's inconsistent with the current satellite data. And a way of stating the current constraints is that at this kind of what I'll call minimum halo mass scale of a few times 10 to the 8 solar mass subhalo, current satellite observations are sensitive to about 25% suppression in subhalo abundance relative to CDM. In other words, if you're more suppressed than that, then you don't predict enough observable satellites to be consistent with the data. So now, what does this imply for fuzzy dark matter? This is I zoomed in on the two plots that I showed you in the previous slide. So here I've plotted the transfer function for a fuzzy dark matter particle of 10 to the minus 21 eV. And you see that the cutoff, right, at some characteristic wave number translates into a cutoff in the abundance of halos at the corresponding halo mass. The issue is that simulations, right, detailed predictions for the subhalo mass function in fuzzy dark matter models are extremely uncertain for several reasons. Most pertinently, it's actually very difficult to correctly simulate the Schrodinger-Poisson equation that dictates the collapse and evolution of subhalos in these kind of highly nonlinear environments, like inside of the Milky Way dark matter halo. So what we have are various estimates. So this, for example, this green curve comes from a large cosmological simulation that takes CDM-like particles with an initial power spectrum appropriate for fuzzy dark matter and simulates the evolution. And there are also semi-analytic models, which is this one shown in kind of magenta here. What these do are kind of semi-analytically model the evolution of fuzzy dark matter subhalos, including their solitonic cores after they fall into the Milky Way. So the point is, there's currently about an order of magnitude uncertainty in the fuzzy dark matter subhalo mass function. This is an extremely important area for future simulation work. But what we can do is take the most conservative estimate of this function. In fact, this dashed magenta curve assumes that these solitonic cores never disrupt. So in that sense, it's quite conservative. And then we can run it through this inference framework.
We have 3 minutes remaining.
Perfect, thank you. And so what we get when we do this is a lower limit on the mass of the fuzzy dark matter particle. In other words, the observations are consistent with CDM. And this lower limit comes out to about 2 times 10 to the minus 21 EV, which is quite consistent with other small-scale structure probes, including the Lyman alpha forest, like we were just hearing about. So importantly, these fuzzy dark matter masses, 10 to the minus 21 EV or so, really don't do much for problems like the core cusp problem or the too big to fail problem, because effectively the de Broglie wavelength of particles of this mass are really too small to affect the dynamics, or at least the observable dynamics of halos from the perspective of core cusp. In terms of ultralight axions, this limit can be interpreted as a lower limit on the mass of the ultralight axion in the case of negligible self-interactions, because there were no self-interactions in those simulations that I told you about. This is really important. So subhalo evolution with ultralight axion-like self-interactions is an extremely important area for future simulation work, and it will, of course, change these constraints in detail. So the last thing, just briefly, that I want to tell you about is a different dark matter model. We actually just heard about this in the last talk, of late-forming dark matter, which I was working on with Subinoy. And the idea here is similar in the sense that the microphysics of dark matter suppresses small-scale power. In this case, if a dark radiation component transitions to CDM at relatively late times, then there's a cutoff in halo abundance, and that cutoff is set by how late the transition occurs. So again, right, the Milky Way satellite population gives a lower limit, right, on this effect. And in this case, the late-forming dark matter can form no later than 1 week after the Big Bang. Otherwise, it suppresses power too much. So I'll skip this since I'm short on time and go to my conclusions. So the lack of a cutoff in the abundance of Milky Way satellites down to halo masses of about 10 to the 8 really yields very stringent constraints on the microphysical properties of dark matter. These constraints will continue to improve. We're going to discover many more satellites in coming years. As far as fuzzy dark matter, masses lighter than 10 to the minus 21 EV are robustly ruled out, but there are large uncertainties in the subhalo mass function that have to be nailed down in order to go beyond placing these conservative limits. So thanks, I'll stop there. I'm happy to take questions.
Okay, thanks, Ethan. So we can take questions. If anyone has questions, you can raise your hand in the participant window or say so in the chat window.
So I have a question. So now with this ULA dark matter not solving the core cusp problem, so it doesn't seem like it is different, at least in small scale, anyway different than CDM. Is that the conclusion? Because the satellite problem is no more a problem, as you said. So what is the motivation looking for this signature? Do you have any comment?
So on the scales that I'm talking about, I agree that there's effectively the dark matter effectively has to be cold. So even if it is fuzzy, right, it can't manifest in observable differences on these scales. But of course, you can always go to smaller scales and look for the differences there. I will say that like structure formation in kind of like realistic ultralight axion models is much more rich than these kind of phenomenological fuzzy dark matter models. So I think there, like I was saying about the self interactions, I think there's much more work to be done to robustly nail down those predictions, right, for realistic like particle models. Okay.
Okay. Any other questions? Okay, there do not seem to be any more questions. So thank you, Ethan, very much.